So you want to learn calculus? Well, you've come to the right place. In this video, I will cover all calculus concepts at a level students in early high school and possibly even earlier can comprehend. So you see all these symbols here right now, and I know that they look really frightening, but soon we'll learn them all and, well, you can brag to your friends. So without any further ado, let's get started. So this is part 2 of this series. I'm very glad you are still here. And in this episode, we are going to be looking at vectors. And since there's a lot to cover, I've decided to split this into multiple parts, where this part is going to discuss the basics of vectors. The second will begin discussing vector operations, and the third will be about vector functions. Now, with me throwing this word around, it sounds so fancy, right? Vectors, and yet I haven't even explained what those are. So, well, we can think of vectors as numbers. So it's just a number, like 3, 4, 5, we know numbers. So you can think of it as just a number that has both a magnitude and a direction. So even that sounds complicated. So let's look at a concrete example. So let's say I want to go to the store. Let's say me, from last episode, I want to go back to the tomato store. I didn't buy enough for my pizza. But this time, I forgot where it was. So I asked my parents, hey, do you know the directions to the store? And they tell me it's 2 kilometers away. Well, that's not very helpful. I could walk 2 kilometers this way and then end up 4 kilometers from the store because the store was in the opposite direction. And that is why we need a direction. That's basically what a vector is. The distance to the store, that's going to be 2 kilometers, and tells me what we call the magnitude or the length of the vector. And the direction, which here would be east, the direction would be telling me, well, its direction. And really, we think of vectors as arrows, and we draw them like that too. It has a length, which we just call its magnitude, and it points somewhere, which is just going to be its direction. Its direction is here. Now, there is one misconception, which I'd like to clear up now, which is that the location of where the vector starts doesn't really matter. So when I draw a vector here, or when I draw a vector here, these two are the exact same vector. So let's say that the length is the same. The length of these is the same, and the direction that they're going is the same. And that means that they're just the exact same vector. It's like drawing a number, right? I could be writing a number 5 here, or I could be writing a number 5 here. These are still both of them 5. They're still both 5. Just because I wrote it at a different place doesn't make it a different thing. And now I'm going to be introducing a little bit of notation so we can actually begin talking about vectors. Don't worry, it's nothing too complicated. Let's just say I'm going to have a variable. This variable is going to be called x. And then I'm going to draw an arrow on top of it. And that's all. That is the symbol for a vector. So this is a vector. So this is unlike your other variables like a, b, or c, where you just set it to a number, right? 1, 2, 3. Here this time we have this arrow on top of it, which makes it a vector. Now, you'll find that in many online sources, they will also, instead of drawing this arrow on top of it, because some of these sources, they can't draw arrows on top of letters, and instead they will make the letter bold, which will basically be like, it will be a bolded letter, and then this will be representing your vector. And that's just a different way of writing it, but here we're going to be using the arrow. Okay, but now that we have this vector, well, what is it equal to? Now, there's many ways to write this. Starting off with an example that you see in everyday life, I could write this as 5 meters north. This would already be a vector. Or I could also write this as 2 meters, 30 degrees east of north. This would also be itself its own vector. It would just be if you draw your east, north, south, west, this would just be 30 degrees east of north. This would be your vector with a length of 2 meters. That would be your vector. Or I could say it's 10 meters left. Of course, then you would need to define like what left is, but that's also a vector. Or I could even say it's equal to 1,000 meters up. Then it would just be up 1,000 meters. All you really need to do to specify a vector is where is it pointing and how long is it. Now in mathematics, we don't often write a vector like this. In physics, you'll often see it written like this though. Don't get me wrong. In physics, you'll see it written like that everywhere. But in mathematics, you don't really write it like this. So instead, let's go back to our old friend, the Cartesian plane. 2 dimensions for now. So you have your x-axis, positive x-axis, you have your positive y-axis, and you have the 0. Now, we know what a point is, right? In this 2-dimensional plane, a point is just given by a pair of numbers. I have xy is equal to 1, 2, or 2, 2, or it's equal to 2, 1. So, in fact, these points can actually be viewed as vectors. That is, basically, let's say I have a point, 1, 2, 1, 2. I can express these points as a vector that goes from the origin towards and ends at the point. And specifically, we call this kind of vector, we call this a position vector. Now, I know what I said at the beginning. I said that where a vector begins doesn't matter. But that's not exactly true here, because here we're talking about a special kind of vector. Now, if you're just focusing on this vector itself, I could be drawing this vector here, as long as it's still just 1, 2. I could be drawing this vector here, and it still would be the same vector. But this one just wouldn't be called the position vector anymore. Now, in mathematics, we often actually use vectors and points interchangeably. So for instance, rather than writing a point, xy is equal to 2, 3, what we will instead do is we will define a vector. A vector, we'll write this one to be v for vector, is equal to 2, 3. And these definitions, they are completely interchangeable. As long as I say v is a position vector, then v would just be equal to this. This would just be v. And people often will write points like that as well when you get into that higher level of mathematics. And here, of course, is just a vector that goes 2 in the horizontal and 1 upwards. So now let's look at a couple of examples. So we've done all this, let's look at some examples. Careful not to erase my plane this time. Okay. So let's say I've got some position vectors. X vector is equal to 3, 4. X vector is equal to 2, 3. Or x vector is equal to 1, 3. Do you think you could draw what this looks like on the plane? On our plane right here? I'll let you have some time to think about this. How would I draw these things? Well, let's look at it. The first one. X is equal to 3, 4. So this tells us that it's going to go 3 units right and then 4 units up. And it's going to start at the origin because it's a position vector. So that means that it's going to go to 3 and it's going to go to 4. You're going to have a point here, and this is going to be what your vector ends up looking like. This is going to be x vector. Let's call this 1, 2, 3. So this is going to be x vector 1. What about this one? Well, in this one, we know that it's going to go 2 units right and then 3 units up. So unfortunately, we need to, oh no, where did my x-axis go? So this time it's going to go 2 units right, and it's going to go 3 units up. Let's erase this forward. So in that case, this is going to be x2. That's going to be what your x vector 2 looks like. And then the last one, I think you can already guess it. This is just going to go 1 unit to the right, 1, and then it's also going to go 3 units up, 3. And that's going to be what that vector looks like. And really, this doesn't really matter what point it is. I could, so far, all of these points, they're just in the positive x, positive y quadrant. But I could also have a point here, like let's say like 3, -5. And then it would just be the same way. I would just draw a vector like that. It's just a vector going from the origin and then goes to that point. Now, if you got all of these correct, great job. But if you didn't, don't worry. I'll post a bunch of practice problems of this in the description. But now I've got a different question. Say I've got this vector. X vector is equal to 3, 4. We know how to draw these now. It's going to be 3, 4. It's going to be a point there, and then we draw it. In fact, let's actually make this a little bit bigger. So let's enlarge this. Same vector is just going to be 3, 4. And do you think you could tell me, so this is this vector, do you think you could tell me how long is this vector and where is it pointing? Well, Well, we know that it goes 3 units right and 4 units up. So we could draw these lines. We could draw a horizontal line and we could draw a vertical line. And this is going to be of length 3. And this is going to be of length 4. We also know that this is a right angle because going right and going up are at right angles. Now, does this look familiar? And that's right. It is the Pythagorean theorem. Remember that for a right triangle, we have a right triangle, A, B, C. You've got A squared plus B squared is equal to C squared. And since length can't be negative, you just have C is equal to root A squared plus B squared, right? It's your standard Pythagorean theorem to determine the length of your hypotenuse. So that means here, the length of our vector is just going to be C. Here, this is going to be A, this is going to be B, and that tells me that C is going to be root 3 squared plus 4 squared. This is going to be square root of 9 plus 16, which is going to be square root of 25. What square root of 25 is going to be 5. Now, the notation that we use to write the length of the vector is often just the absolute value of the symbol around the vector. So this is the symbol for the vector, it's x, and then we just write an absolute value around it. Now, many sources will also add an extra line. They will write it like this, where you have these extra lines. But we're not going to do that here. We're just going to use this notation. So we've got x vector is equal to 5. But what about its direction? Do you think you could tell me the direction that this vector is pointing? Well, we know that there's going to be some angle. This is going to be a positive x-axis. There's going to be some angle between our vector and the positive x-axis. We're going to call this angle theta. Now, we know from SOHCAHTOA, if you've studied trigonometry in the past, we know that tangent of theta is going to be the opposite divided by adjacent. So it's going to be 4 over 3. That means that theta is going to be arctan of 4 over 3 or tan inverse. And this is just going to be approximately 53 degrees. Approximately. And with this, we're allowed to say that this vector, x vector is going to be 5 units, and it's going to be 53 degrees counterclockwise from the x-axis. So from the x-axis is going to be implied when we don't write it. So it's just going to be, we're going to write it as 5 units and 53 degrees counterclockwise. And now this way of defining a vector, this way of defining it is known as the polar representation. While the other way of defining it, this one, x vector is equal to 3, 4, we call this the Cartesian representation. This is going to be the polar representation. So now that we know how to define, draw, and measure vectors, let's look at a couple of examples. So erasing all of this. Let's say that I'm in my bedroom. I'm in my bedroom. There's my bed. Not a very good bed. And let's say that I'm just walking to my door. My door is over here. And let's say that the distance I walked was 50 meters. 50, oh no, not 50. 5 meters. With an angle of 30 degrees. So this is going to be an angle of 30 degrees. Now this gives me a vector. Now do you think you can tell me the polar and Cartesian representations of this vector? Well, the polar representation is already basically given to us. We're going to define our positive x-axis to be here, positive y-axis is going to be upwards. Now, this is going to tell us that this, which I'm just going to write as x vector, this x vector is going to be 5 meters, and it's going to be this time 30 degrees clockwise, right? Because now we're going this way instead of this way. We're not going this way anymore. Now we're going this way. So now we're going to be 30 degrees clockwise. Instead of writing 30 degrees clockwise, so another thing that mathematicians also often write is negative 30 degrees, where when we write a positive angle, it's implied that it's counterclockwise, and it's a negative angle, it's going to be clockwise. But now, finding the Cartesian representation of this is a little bit harder. So we can draw a vertical line from our vector, and this is just going to be our horizontal line, right? This right here is going to be a horizontal line, and we've got a vertical line. Now we know that this is 30 degrees, and we know that this is going to be 5. If you've done some trigonometry in the past, you probably already know how we're going to do this. So we know that the length of this right here, is going to be 5 cosine 30 degrees. That's going to be about 4.33. We know that the length of this is going to be about 5 sine 30 degrees. That's going to be 2.5 meters, because this is all units, right? So that lets us write this vector as also 4.33 negative 2.5 meters. And that's going to be the Cartesian representation for a vector. And here it's negative 2.5 because our positive y-axis was that way, and this vector is going the negative y-axis, right? Still positive, but now, still positive x, but now it's just negative y. So that's why we have to write negative 2.5. Now let's look at one more example before we wrap up. All right, so let's say that I threw a ball at a wall. So I have a ball, this is going to be a wall, and I threw a ball at it. It hit the wall, and the wall is 2 meters away. So we're going to say that this wall is 2 meters away. That's going to be a positive x-axis. That's going to be a positive y-axis. And then I threw this ball, and oh, it hit here. And let's say that the angle from here to there is going to be 45 degrees. now that I have this, do you think you could draw a vector that represents where the ball went? And could you also tell me the polar and the Cartesian representations of that vector? Pause the video here so you can try to figure out the answer yourself. Well, let's think. Where did the ball start and where did the ball end up? So it might be better to draw my axis over here. This is going to be my 0, positive x, and positive y, right? So this tells us that there's going to be a position vector that's going to be going from me to where the ball landed on the wall. Oh, vectors can't be curved. This is going to be a position vector. We're going to call this vector x. So this is going to be the position vector, and we know that there's going to be a horizontal distance. There's going to be a horizontal distance for this vector. And this horizontal distance is going to be 2 meters. We also know that there's going to be an angle, which is going to be 45 degrees counterclockwise from the x-axis. And from there, it's just going to be trigonometry. From SOHCAHTOA, we know that, let me erase here this so I have more space to work. We know that the length of x, or 2, divided by length of x, is going to be cos 45 degrees. Right? Adjacent over hypotenuse, right? So that tells us that the length of x is going to be 2 over cos 45 degrees, which is just going to be 2 root 2. We also know that tan 45 degrees is going to be opposite divided by adjacent, right? So if we call this, we're going to call this y naught. It's going to be y naught divided by 2. And that tells us that y naught is going to be 2 tan 45 degrees. And this is just going to be equal to 2 because tan 45 is 1. And now that we have this, there you have it. This is going to be 2 meters. And we already have the polar and Cartesian representations of our vector. We have that x vector is either equal to 2 root 2 meters, 45 degrees. Again, remember when we don't, it's going to be positive 45 degrees because it's going to be counterclockwise. And the Cartesian representation would just be 2 meters. So with this, let's wrap up. All right, so today we talked about the basics of vectors. Why we need them. Vectors are just, they have a length which is v, and they're going to have a direction theta. We talked about why we need them, because of course when I want to go to the store, just telling me the length, not very helpful. Telling me the distance or telling me the direction might be a little bit more helpful, but if it's 2,000 kilometers away, I'd rather not walk all that. And we also learned the 2 ways of writing them. We learned the polar representation, which is just written as v vector times theta, or not times theta, theta degrees. Or we also learn the Cartesian representation, which is going to be written as v vector is equal to 2 points, or is equal to a point, xy, where this is going to be your x, this is going to be your y. And that's all from me. I hope to see you in the next video where we're going to be talking a little bit more about the advanced parts of vectors.